Sorry. Oh, no, it's fine.
And so do you hear me all?
Yes.
Okay, thanks. So I wanna, that's my first slide. So I want to introduce co-authors and contributors of this work. The list is quite long, and I show only some fraction of those contributors, which contributed most more than others, but the entire team was close to 60 people. And that's this a long list, so kind of I'll show only some of them. So the objective of this work is to present preliminary results of observation made on boundary layer mixed phase clouds with a cloud top temperature warmer than -9. And the data were collected during the in the high Arctic during the Arctic 6 flight campaign. This work was primarily focused on cloud cases with challenging cloud microphysics. Challenging is the keyword, which cannot be directly explained in the frame of our current understanding of how cloud work. The overall purpose of today's presentation is to show the material and to inspire reconsideration of any existing microphysical stereotypes and cliché, and stimulate further studies of Arctic clouds. Arctic is a NASA-led field campaign with an overarching goal to quantify how surface properties, clouds, aerosol, and precipitation contribute to the Arctic amplification, explore summer surface radiation budget and sea ice melt during early melt season and during summertime. The goal is to advance our understanding about rapid Arctic climate change and improve satellite retrievals. The flight operations were conducted out of Pituffik, former Thule, during two deployments in May, June, and July, August 2024. The Arctic field campaign involved data collection from 3 airplanes, which you can see here. It's NASA P3 and Learjet. The operations were focused on measurements of at low altitudes, sampling cloud microphysics, aerosol, CCN, INPs, performing radiation measurements, and remote sensing. The G3 at the bottom here, Gulfstream 3, was operated at high altitudes, performing remote sensing of the same clouds where P3 and Learjet were operated. So we aligned those flight operations along the same line. The microphysical instrumentation on P3 and Learjet are showed in these two tables. So as you can see, this is a state-of-the-art probes, and some of them are new, just with those asterisks. And so that's a debut of these instruments, and I should say that's our just great instruments, and I'm just absolutely happy about just be part of this. And I should also mention that that Learjet had a K-band radar installed on this. It's pro sensing radar. And again, so basically these these instruments are mirroring on both aircraft, so they were just very similar, and the analysis was also equivalent. So for the characterization of cloud environment, the following flight pattern was involved. So the horizontal flights above, inside, and below cloud, and purposing through the cloud were focused on sampling and characterization of aerosol, microphysics inside, and the vertical profiles of this the cloud microphysics. So that's kind of the this flight pattern we adopted for the entire field campaign. The diagram on the left shows the area of sampled clouds. You see, just it's over Lincoln Sea, just above the Ellesmere Island and Canadian archipelago, and so we just went kind of pretty far away. So red and blue shows the area sampled by in low-level stratiform clouds by Learjet and P3. The total length of sampled cloud was close to over 12,000 kilometers. The length of in situ sampled clouds were over 6,000 kilometers. The fraction of mixed phase of these 6,000 kilometers was approximately 60%, and liquid clouds of these 6,000 kilometers were close to 40%. The cloud measurements were performed during 19 research sorties, of which we did 271 profiles. Altogether, this makes the ARC-6 data set on the Arctic boundary layer clouds the most comprehensive. There is a here is a statistics of ARC-6 clouds, sampled clouds at temperature below -9 and altitude below 3 kilometers. So the top three diagrams show the liquid and mixed phase clouds, and the bottom ice, which were sampled inside those mixed phase clouds and precipitating out. So as we can see here, the droplet, approximately 70% of droplet concentration were less than 50 per cc, which is indicative of low aerosol load, and so similar measurements were reported before. Because it characterized that says that the Arctic environment is pretty clean. So this reduced the competition for water vapor between droplets, and they grow to larger diameters. You see that the effective sizes in those clouds were pretty large, which is favorable for formation of drizzle, which was frequently occurred in our measurements. And 90% of clouds had liquid water content less than 0.3 gram per meter cube. So it's but the highest what we measured was surprisingly pretty high, 0.8 gram per meter cube. So about ice clouds, so what we see that majority of ice clouds had ice particles had concentration less than 5 per liter. So all non-ice clouds were excluded from these statistics in these three diagrams. Liquid water content was mostly less than 0.0, ice water content was mostly less than 0.05 gram per meter cube. And as expected, low ice water content clouds were associated with a single ice crystals, and large ice water content, usually below the cloud base, were mostly associated with the aggregates. So the concentration of aggregates for high ice water content was larger, or dominated by aggregates. So the maximum size of ice crystals was extended up to 1 or higher than 1 millimeter, up to 2 millimeters, which is outside of this range. And most cases with large ice were associated with the aggregation process, and small ice crystals were just all our measurements were dominated by crystals smaller than 500 micrometers. That was diffusion grown ice crystals. And the dominating form of actually almost all ice crystals were either columns or needles, and with sometimes we saw observed gropal as well. Just I should say that there were a number of previous studies of in situ microphysics in the Arctic, and so the list of those observations just here. So if it's pretty long, and if some publications are missing, just please forgive me for that. So the main message from all this previous in situ observation is that observation of mixed phase clouds in Arctic is quite typical. And so what the right diagram shows the product of clouds at Calypso, which shows the iciness of mixed phase clouds with cloud top temperature warmer than -6, thanks to Lorenzo Zamorov for providing this data. And you see lots of yellowish and light bluish colors, which is indicative of this presence of ice in those stratiform clouds. So let's start rolling with the results. So boundary layer cloud. So this diagram shows kind of temperature and altitude during sampling. That's liquid water content ice and Dmax. And boundary layer clouds are characterized in many occasions, and they were just well documented that by high inhomogeneity of spatial thermodynamic phase. For example, this diagram shows a sequence of liquid and mixed phase clouds highlighted by blue and yellow colors. You can see here, and in those liquid cases that you see, this is a 2D gray data. That's no ice. You see small dots, which are droplets. And you see those ice crystals in between in mixed phase layer. It's also 2D gray data. And so you see that the spatial the horizontal spatial distance is may extend from tens of kilometers down to hundreds of meters. So there is a high intermittency. So that's on this side you can see profile, and the cloud top temperature here was close to -4, and you see just that's a pretty high concentration of ice crystals, which are shown here, which goes up to 30 per liter. So this observation raises a question: why in a seemingly uniform cloud layer does ice form and persist in one segment of cloud, yet it is absent in others? I'm not sure if any current cloud resolving model can reproduce the observed phase heterogeneity of at such warm temperatures. So this slide shows the case of mixed phase cloud where ice form at temperature above -3.5. So you can see this red line. So the scale is here on this side. The cloud was kept by temperature inversion, which temperature was above freezing point, which excludes the seeding from above. So all this ice was formed inside this relatively thin layer. And the concentration of ice particles was up to 6 per liter, which is pretty high for this temperature. And it cannot be explained by heterogeneous nucleation of INPs. Its temperature is extremely high. Therefore, it should be the only way to explain it is to attribute it to secondary ice production. However, there is no gropal. Just you can see this is a HUPS data at 50 micrometer pixel resolution, and that's high resolution 2D gray data. And you can miss it in 2D, but the sampling volume is pretty high. And if you see any gropal, it just show up on HUPS data. And which is necessary for Hallett-Mosse process. So Hallett-Mosse process is excluded. And the droplets were too small. You see these tiny small dots, so there are no just any SLDs or drizzle size droplet which are favorable for freezing or fragmentation of freezing droplet mechanism. So the mechanism responsible for formation of ice in this extremely warm layer is just absolutely unclear. Other SIP mechanisms are just obviously not relevant of those which we recognize as SIP mechanisms. And this raises a question where all this ice comes from. So this slide shows comparison of microphysics in two cloud segments highlighted by these gray strips. So you can see that's the same sequence of variables as in previous diagrams, temperature and altitude, liquid water content, ice concentration, and a maximum size of ice. What is interesting about this case, the environmental conditions in these two cases are very similar to each other. So the temperature is the same, liquid water content is the same, the droplet number concentration is very close, but these cloud segments were separated by 10 kilometers. Both cloud segments had gropal. In segment one, in this one, so which is shown here, we see that many ice crystals between gropal size, and you can see gropal on the HUPS. So that's HUPS, and that's 2D gray, the same as here. And this is consistent with the Hallett-Mosse secondary ice production. However, in segment two, we see a multitude of gropal, so just lots of gropal here, but no ice. This suggests that secondary ice SIP is not active in this cloud region, even though the Hallett-Mosse criteria was satisfied. So this raises a question about our current understanding of the environmental conditions when Hallett-Mosse mechanism is active. So that's really kind of striking observation. Next case shows descent through approximately 1.8 kilometer deep multi-layer cloud system. So you see the K-band radar return on the bottom diagram. Here, the upper 800 meters, so they are not visible here because the cloud extends up to here, but it's not visible by, there is no cloud return due to sensitivity of the radar. And the cloud was cloud temperature top was about minus 10. So you see the temperature profile here. The upper 800 meters, so it's maybe you see on your screen, it's a bluish color here and a yellowish color here. So the upper 800 meters were in liquid state with a drizzle forming in this area, and lots of SLDs, and just I'll show in this next slide. What is interesting about this case that the first ice was observed at higher temperature, at around -6, much lower than the colder cloud top. And just again, so the question why ice wasn't formed here, because the condition seems to be more favorable for ice formation near the cloud top rather somewhere in the middle. So this slide is a continuation of the previous one. So the same, you see the same profile, but just on the left side, I show the images of those cloud particles sampled and just in the region indicated by these arrows, 1, 2, 3, 4. It's accordingly 1, 2, 3, 4 here. So just in the upper part, so is you see lots of SLDs, but no ice at all. And first ice forms somewhere here. Just you see these tiny small ice crystals indicated by these red arrows, and they evolve to bigger ice, and 3 it's a lower level, and you see that drizzle is growing, which is suggestive that all these the entire cloud was microphysically connected from the top to bottom. So as it progressively connect, just you see that droplets are growing. And later on a lower level near the ground, so you see just formation of lollipops, and ice is a little bit bigger, but it's not much. So this what is interesting that the drizzle is a form like 200-300 size diameter drizzle based on laboratory studies create conditions which are favorable for formation for initiation of secondary ice production due to fragmentation of recent droplet mechanism. And it is expected that the presence of this drizzle will ignite the formation of first ice, will ignite a chain reaction, and for formation of secondary ice. However, we don't see it. So, and we don't see drizzle as well. So it's kind of the question is why SIP is so inefficient here. What are the other parameters controlling secondary ice production? So I'll switch gear so to remote sensing. The past remote sensing observation of mixed phase stratiform cloud showed that cellular structure of radar returns is quite common, and this is suggestive that ice production occurs inside those cells. And during ARC-6, the LRJet instrumentation allowed simultaneous remote sensing and in situ observation of the spatial inhomogeneity in mixed phase clouds. The diagram on the left, so it shows kind of just lots of structure, cellular structure inside. So, and this is a zoomed in diagram, which shows the K-band radar return and simultaneous ice water content measurements. So the separation between these two measurements were about 200 meters, which kind of you just assume that they kind of that they are related, and in fact they are related. You see peak-to-peak correlation between ice water content and those radar return, and the size. So that's a scale. The characteristic size of those cells where ice is forming is of the order of few hundred meters. So that's kind of quite small cells, and despite that, the cellular structure of ice formation is well recognized. There are lots of publications in the past about that, and but the mechanism of ice formation in these cells remain poorly understood. And the collected data during the ARC-6, we have lots of data like that, provide insight into the conditions favorable for enhanced ice production in stratiform clouds. So this diagram shows the time series of extinction. So that's kind of another slide about cellular structure of ice, but instead of radar, so this is a P3 data. The previous was LRJet, this P3. It shows the correlation between Marley, it's Raman LiDAR. Thanks for Gen 1 providing sharing this data with us. And so that's a LiDAR return. And it's you can see peak-to-peak correlation between those bright yellowish and green areas, and with extinction, ice water content, and ice concentration. So, and that's kind of a type of ice. This was a sample below. It's a precipitating ice below the below the cloud base. So this slide shows another example of cellular structure, but that shows the another extreme. Two slides before, two previous slides. For example, here is a kind of the scale of those cells was larger than in in the previous case. It's the 10 kilometers is here. So you can see that the size of those cells is of the order of kilometers. Here, hundreds of meters. And that's another extreme where we just, this is a two-layer system, and we sample it along this pattern. So that's a top view of the Learjet track. And so what we see that we were lucky to spot those two big cells of ice formation separated by 100 kilometers, 110 kilometers between them. So all these clouds in between were liquid. We made a circle, and there were two generating cells, and the ice was forming in the upper layer. So if you just kind of the question, what are the conditions controlling ice initiation in a seemingly horizontally uniform stratiform layer? Why ice generating cloud regions were separated by such large distance, and what are the conditions controlling this? So this this slide is show the zoomed in cell number 1, which is shown here. So you see these two layers, which is indicated by these grayish colors. And when we zoom in, so you see lots of internal structures inside those cells again. So, and I want to just point, pay your attention on this small region with the enhanced concentration of ice. So that's only 300 meters wide area with extremely high concentration, and the temperature here was about minus 3, minus 4, and that's only small ice crystals. It's basically diamond dust, and on HUPS data doesn't show presence of any gropal here. There is some ramin, minor ramin, but no gropal. So so this brings a question: what seed mechanism produce such high concentration of ice, and why it's so localized? And and we see these nested structures of structure of ice formation on and on and on. So what we see this spatial heterogeneity of thermodynamic phase and cellular structure, and so kind of all variety of microphysical patterns. In most of previous studies of secondary ice production, the focus was on observation of high concentration of ice crystals. But I want to pay you attention that low ice concentration is equally important. But in my opinion, this observation was this type of observations were overlooked. So that's we were purposing and doing horizontal. So this diagram shows how just the sampling of cloud during purposing and horizontal legs. And so it was quite very well uniformed cloud layer. And so what we see here, so that's a profile, and that's horizontal leg here. The temperature was about minus 3 degrees C. And so you see lots of ice on this, on the left side of this diagram, and very, very little ice here. So just that's this diagram shows a lonely ice crystal, like a lonely cowboy in prairies, and so nothing around. So and the ice crystal is quite small. So what is this ice crystal? Is it result of primary ice nucleation, or is it somehow just horizontally shifted, transported ice from this area? But why it's so small then? And so there are many questions. And so if what is this SIPO PIP, and where this ice is coming from? So and I think this type of observation may shed light on primary and link between primary and secondary ice production and formation of primary ice. But do we have a capability for that? So the challenge of conducting primary ice production observation is related to the fact that the concentration of INP is well below sensitivity threshold of particle probes, as shown here. So, for example, the thresholds for 1 second sampling for 2DS and HUPS type instruments is ranging from 0.01 to 0.001 per liter. And so there is just lots of data which are missing by conventional particle probes. And so it brings again, so lots of question. What is there is a obviously related some hidden period of ice development before it ignite, generate secondary ice production, and the sample. Those ice can be sampled by and visible by our instruments. So what is the time scale? Characteristic time scale between PIP and SIP? Is it kind of a fraction of seconds, or just seconds, or minutes, hours? So again, so we don't know that, and that's kind of one of the questions which should be addressed and focused in the future research. My next slide is related to observation of primary ice production, and we should give the gear to discussion of INP measurements. There is lots of previous studies suggesting that that local origin of mineral dust may explain the observed ice concentration in the Arctic clouds. And there is a growing evidence of biogenic and organic INP originating from marginal ice domes, like what are shown here, and melt ponds, which are active at temperature close to the freezing point. And this diagram is depicts different sources of INP in the Arctic. It can be large long-range transport of INPs. It's land sources or blowing ice. So that's Papa Constantino in 22 employed DAR data set from CloudSat Calypso to explore the effect of ocean surface on ice concentration. They found that low ice in the Arctic clouds, low-level Arctic clouds show larger quantities of ice crystals over sea ice than over the ocean. However, this finding contradicts a previous hypothesis, which stated that more ice crystals would be possibly formed over the ocean because of presence of high highly ice effective aerosol there. So like sea spray. So and in these regards, to address this question, we just look at ice concentration over different surfaces, over solid ice, broken ice, melt ice, and over open ocean. This map shows the P3 and Learjet flight tracks over different types of ocean surfaces. Most of the spring season were observed over solid ice, whereas like here, whereas summer season clouds were observed over melt ice. You see just green and blue. So for the ARC6 data set, we did not find any significant difference. So between spring and summer clouds. So this table shows the mean concentration of ice particles during spring and summertime, summer deployment. It's kind of, they close to each other. And the same refers to max size. So, but kind of max ice concentration, maximum ice concentration. So it's kind of, they pretty much close and within the statistics of collected data. So to continue, so this the diagram on the left shows one of the most striking cloud microphysical results from the ARC6 campaign. It shows the mean, the average ice particle concentration as a function of temperature. And as seen, the average concentration increases with increasing of temperature, peaking between -3 and -4, and then drops. The maximum ice concentration agrees with the Hallett-Moser process temperature range. However, as we saw in the previous discussion, that Hallett-Moser process were not satisfied on many occasions. The conditions related to that. What even more striking is that the trend. So if you just overlay this data on the INP concentration versus temperature, it's a classical dependence of INP concentration versus the temperature. So the trend is different. So that's kind of shows the way of changing. So and we saw many clouds at colder temperatures, and one of the examples was shown in one of the slides. So low temperature clouds were not always contain ice, which is quite interesting. And so it brings lots of questions. So because it's the trend is opposite to the classical behavior of INP concentration versus temperature. And so this raises question about consistency of INP measurement techniques with the process involved in ice formation in natural clouds, such as mechanisms of primary ice formation. Are they the same as in INP instruments? And the time scale of primary ice formation, it's related to deterministic versus stochastic. Secondary ice production obviously is not involved in INP measurements. Residence time of ice, circulation of ice, and other ice processes, which are kind of, and in this regard, I would put the question in a broader context. Because of the difference in mechanism involved in INP measurements and ice particle formation in natural clouds, would it be relevant to compare concentration of ice particles with those measured concentration of INPs? So do we just by trying to compare ice concentration with INP, are we comparing apples and oranges? So it's so that's my final slide with the conclusions. So we sampled during the Arc6 campaign. So we sampled roughly 12,000 kilometers of Arctic boundary layer clouds, and we explored them in situ and remotely. And 60% of these clouds were in mixed phase. And observations showed a variety of macrophysical patterns in cloud regions identified as SIP affected. And the next conclusion I would put in bold: some of the SIP microphysical patterns cannot be associated with recognized SIP mechanisms. So we have to think about what are the other potential mechanisms. And so there are just urgent questions related to that. What are the source of INPs, and what the role of local long range transport of those aerosols, and what's the role in ice formation? What type of, is it mineral, organic, biogenic, or any other? And what is the relation between SIP and PIP and those extremely warm clouds which we observed in the Arctic? And I want to stress the lack of laboratory studies. They are growing, but still not enough. So the answer about the SIP mechanism is related to the second bullet here, and about direction. So that's it, and so that's a literature, and so some of these results were published, presented in this talk, was published in this in the ICP paper. And thank you very much. And I would like to acknowledge the aircraft crew on 3 airplanes. It's a very high cooperation, NASA support personnel, project directors and PIs, and the entire Arc6 team, which made this field campaign overwhelmingly successful. So that's it. Thanks.